Très bien. Donc nous allons commencer notre session de cet après-midi en accueillant le professeur David Shoemaker, qui est professeur au MIT et directeur de Advanced LIGO, qui est aussi, à ce que je comprends, francophone et francophile. Et puis, il va nous parler de la détection des ondes gravitationnelles.
Mais malheureusement, je vais parler en anglais plutôt que français. Je pense que ça va être plus net comme ça. So my notion here is to talk a bit about the fundamental physics behind our measurement, as well as talking a bit about the result of the measurement that we made. And it's been very nice to have the introduction of Thibault and Henri beforehand, because it puts into context a number of the things that I'm going to talk about, and will allow me to jump over a few slides. Let me first jump over, say, the first 20 years of my work in the field by saying that Virgo and LIGO proposed and received funding for and then built two infrastructures in the US and one here in Europe. And we built instruments to go in them, and they performed as well as we hoped they would. We observed with them as we wanted to, and we saw no signals. This wasn't a shock to anyone. I think that we all thought that it was plausible that we could see signals, but not probable. And in both Virgo and LIGO, we came to the situation with the plans to always enable further advances. And so that's mostly what I'm going to be talking about. Oops, okay, good. A slide that likes to be jumped over. Here we are. So we had proposed then to put advanced detectors in these same infrastructures. And a thing that's, well, during the time that we were observing with the first instruments, we had an R&D program that was really quite active around the world. And we had chosen a design that would be 10 times better than the sensitivity that we had for the initial detectors. And the thing that's really important to understand is that we measure amplitudes with these detectors, not power. So if we increase our sensitivity by a factor of 10, increases the volume of space we can reach by 10 cubed. And so that makes an enormous difference in the likelihood of seeing a signal. The number of candidate objects within our reach goes up by a factor of 1,000. I think you've already heard about the notion of our measurement technique. We saw Henri's nice animation of the ring of free particles that's distorted by the passing of a gravitational wave, and the notion that you can put a Michelson interferometer in that arrangement and make a differential excitation of the two arms, which turns this optical instrument into a transducer, one that converts strain in space into an electrical signal at the output of this light detector. The numbers are still really scary, though. The magnitude of a typical signal that we could hope to see, say, once a month or so, is on the order of a strain of 10 to the minus 21, a delta L over L of 10 to the minus 21. And to give you a notion, that's resolving the thickness of a human hair over the distance from here to the closest star. So the magnitude of the measurement challenge is really quite something. But I'm going to tell you a bit about the limits to our measurement and give you a notion of how it's possible that we can make this measurement. I will note that the arms of these instruments on the Earth are short compared with the gravitational wave wavelengths. You can calculate that if you assume, as Einstein did, that they travel at the speed of light. Then you can calculate from the frequencies that we're looking at, which are sort of audio frequencies, 100 hertz, that the wavelengths are hundreds, thousands of kilometers long. So our instruments are short, and the longer we can make them, the larger the delta L is that's associated with a given strain H. And it's only limited by taxpayer noise. We would have longer ones if we could. So what are the things that limit us? The first one thing I want to talk about is shot noise. At the output of this interferometer, there's a light beam that arrives, and the photons are distributed with Poisson statistics. And as you know, the more particles that you have per unit time with Poisson statistics, the smaller the fractional fluctuation. So the objective is to have lots of light. It's interesting to notice that Einstein was the first person who really put this in a form that made some sense to us as modern physicists. And then the scaling law, the fringe resolution improves as the square root of the laser power at high frequencies. I'm going to show you a lot of these graphs that show you the strain. This is the fractional length change in a 1 hertz integration time versus frequency, where that's 100 hertz, that's a kilohertz. This is sort of the range of notes on a piano or so. And so at high frequencies, we can improve the sensitivity from the initial Performance. I'll mostly talk about LIGO because that's where I come from, but all of these lessons are the same for LIGO and Virgo. You can increase the sensitivity at high frequencies by increasing the number of photons that are coming out, and that sensitivity limit in strain, well, it gets better as the arms get longer, as I said before. It also gets better as you make the power bigger and bigger. But there's an interesting thing that happens at a certain point, and it's relevant to a question that was posed earlier today. As you turn up the laser power, that random arrival rate of photons hitting the mirrors at the end here shake those mirrors. That has a spectrum of 1 over f squared because those mirrors have inertia, but you can make a calculation again for the limiting strain due to this effect, and now you see that the p is in the numerator rather than the denominator. So obviously now you can solve for an ideal power for a given frequency. As you turn up the laser power, you ruin the sensitivity at lower frequencies while you improve it at high frequencies. So now you can find, in fact, that this is a Heisenberg microscope. It's an instrument for which, in this simplest condition, can be seen as an instrument where you meet the standard quantum limit, and you just have to choose what frequency you want, and what mass of mirror you choose to find out the ideal power to use to illuminate your system. It turns out that the way we use our instruments, and I already mentioned this very briefly, is to include a signal recycling mirror here, and it sends some of the output light of the interferometer back in. And what that does is to couple the amplitude and the phase fluctuations and through the motion of the masses. And that leads to Ponder motive squeezing. It means that you modify Heisenberg's, Heisenberg's law still holds true. Delta x, delta p has got to be less than h bar. However, that couples the two, so you can shift between delta x precision and delta p precision as a function of frequency, and it leads to a somewhat more complicated pattern of sensitivity as a function of frequency. But so in the bottom end, the LIGO, advanced LIGO system uses a 200-watt laser. It uses 40 kilogram test masses that holds down the noise at low frequencies and gives us a quantum limited sensitivity, which is quite broad and ultimately will dominate most of the noise when we finish commissioning the instrument. So far, it must be said that we are only looking in the shot noise limited region. We have lots of excess practical noise that hides this radiation pressure noise. So the next limit to sensitivity that I want to talk about is yet another one that Einstein brought to light for us. He did everything in the end. And it's this KT of energy per mechanical mode. Brownian motion is something that you must have heard of. And if you look at it in terms of a simple harmonic oscillator, you can say that the RMS motion of that oscillator goes as the square root of KT over some stiffness that corresponds to the nature of the system. But there's an important thing is that that motion is distributed in frequency according to the losses. And in fact, you can look at it in terms of the real part of the impedance of the system and find that that changes the expression in frequency of this thermal noise. And the thermal noise dominates in our instruments in this region, a crucial region for the detections that we've made between, I don't know, some tens of hertz and some hundreds of hertz. And I'll tell you exactly where that loss is, in fact. The first thing to note, though, is what we know is that there's KT of energy per mechanical mode in integral. But what we can do, using the fluctuation dissipation theorem to our advantage, is to take low mechanical loss materials. The integral under this curve is always square root of KT. However, if we have a very high Q system, that is a very low mechanical loss system, then a lot of the area will be underneath a very narrow peak, and that brings down the noise levels above and below that peak, which is a very nice way of managing this thermal noise. We can have very narrow peaks in our spectrum and look for gravitational waves between them, bring down the thermal noise between those peaks by using low mechanical loss materials. So that's what we do. In LIGO, we have this test mass. Again, Henri showed us this nice photograph of a test mass. It's a 40 kilogram piece of fused silica, very pure, very simple, attached with fused silica fibers to the mass above. And in that way, we make these really narrow, very, very high peaks of Q of 10 to the 8th or 10 to the 7th or so, and then keep the thermal noise low in this region here. The thing that's maybe most surprising, that the coating on the mirror surface, To make a high reflective mirror, you alternate high and low index of refraction materials, and that makes effectively a tuned filter like L's, R's, and C's, which reflects the light very efficiently. The hundreds of microns of coating material on the front of this mirror, something that only weighs tens of milligrams in total, is so lossy. It has a loss of, say, a part in 10 to the 4 per cycle rather than 10 to the minus 4 per cycle, rather than 10 to the minus 8 per cycle. That very, very small amount of material dominates completely the thermal motion because that's just where the laser beam falls.
What is this coating material?
It's made of tantalum and fused silica. And those are materials which have wonderful properties in terms of the optics, very low loss, very low scattering. But it's a sputtered surface. It's an amorphous material, and it doesn't at all have the nice regular features of a solid glass. And so it has this kind of 10 to the 4 worse loss. So that's the dominant limit in the critical 10 to 200 hertz band, and it's there where we're putting a great deal of research because this is really what is going to limit this next generation of instruments. Then comes seismic noise. I don't think that Einstein worked on seismic noise. I think he had better things to do. It comes from motion, the waves on the coast, from people moving around. And what that does, not only does it interfere with the gravitational wave, masking the motion of a gravitational wave due to this external stochastic force at frequencies above 10 hertz where we want to see gravitational waves, but also a really important element in all of these instruments is the controls. We have to maintain the Fabry-Perot cavities within a tiny fraction of a wavelength of light to have the resonance build up. You need to maintain the alignment over multi-kilometer distances to microradians so that the beams still overlap. And all of those control problems are made much, much easier if you can reduce the seismic noise even down to 10-second periods. And so we use in LIGO, we use an active control system. We have seismometers that measure in a very sensitive way the motion of a platform. We develop an electrical signal, send it through an amplifier, and send it to an actuator which holds that platform still. So that stable inertial table gives us a very good rejection of seismic noise in our gravitational wave band, and then down here at lower frequencies, down into the 0.1 hertz or so, very stable system. A last thing that I want to mention is one of the reasons that will cause us ultimately to want to go into space for gravitational wave antennas, and it's one more force on the test masses. We're all familiar with seismic motion, and it sometimes takes the form of compressional waves that run along the surface of the Earth. There are Rayleigh waves that cause sort of a wave-like undulation of the surface. All of these things result in gradients in the density of the material around our test masses. And that material, which is more dense, causes a greater gravitational wave pull on this test mass. And that is something, unlike ordinary seismic motion, that we cannot shield against. And so the mass wanders around in time due to the seismic noise that's nearby it. Well, you can bury the system underground, as our Japanese colleagues are doing, to make a slight reduction. But the spectrum is so deep that you can't really hope to get below perhaps 3 hertz or so as the very lowest frequency you could detect on the Earth's surface. And so if you want to see really massive gravitational wave systems which emit down in the frequency range of a tenth, a hundredth, a thousandth of a hertz, you'll have to go to space. So this is ultimately what will limit the lowest frequencies we can detect on the Earth's surface. And let's see, actually, I've talked ahead of myself a bit. This stochastic force of the gravitational pull varying influences advanced LIGO and advanced LIGO, in the sort of 10 to 15 hertz region. And we may be able to put in an array of seismometers to subtract out some of that. It won't get us very far. But of course, what I've talked about so far are really pristine, easy to calculate fundamental noise sources. And that's not what limits us most of the time. This is one map. This is, again, strain. Actually, this is in meters per root hertz. This is, of course, rather than calling out the H, which is delta L over L, this is talking about the actual delta L that we can measure. versus frequency again. And you can see that we were able to measure a resolution of some 5 times 10 to the minus 20 meters if you integrate for 1 second. So the sensitivity is absolutely incredible, but there are lots of things competing. At high frequencies, actually, we're very close to the shot noise. That's one of these lines here. That's something where we can really do a very good job of rejecting all of the frequency noise and position jitter and mode uncertainty that Henri talked a bit about. But then at low frequencies, there are so many things that mask our signal having to do with alignment systems, excess noise in our sensors and so forth and so on. And the work of commissioning, the work of bringing the instruments to their true value in terms of sensitivity is all about reducing these practical noise sources. So where were we for the first observing run? This is once again strain back to delta L over L versus frequency. This is the best that we ever saw with initial LIGO. And this is where we were for our first observing run with advanced LIGO for the 2 different observatories. They're very similar in their noise performance. Up at high frequencies here, we see about a 3-factor improvement. This is, you'll recall, the region where we're limited by shot noise. And one way of getting this would be to make a factor of 10 increase in the laser power, which square root of 10 is 3. It turns out we actually also improved the efficiency of the optical system. And so that is the improvement here. At these low frequencies, the improvement in our seismic isolation system in LIGO made more like a factor of 100 improvement. And this was absolutely key in making the detections that we did. So here's this nice summary slide that puts a bunch of different timescales together. There's this nice simulation of black holes 1.3 billion years ago, as Thibault was saying. These black holes merged, and it's really fun to note that that's about the same time that multicellular life was starting to form on the Earth. It's 100 years, to within a month or something, after Einstein predicted gravitational waves according to his theory. About 50 years after Ray Weiss invented, he was not the first or the last to invent them, but he was the first to lay out a program which allowed us to get to usable detectors. About 50 years after he did that, 30 years after the National Science Foundation in the United States, MIT and Caltech founded LIGO, and of course similar activities here in Europe for Virgo. 10 years after advanced LIGO, a second impulse of funding from the National Science Foundation, even though we had seen nothing with initial detectors. And about 6 months after we started doing our detector tuning, pushing down that 20 or 30 noise sources at low frequencies, 2 days after we started observing with the initial LIGO, with this advanced LIGO detectors, we saw our first signal. So September 14th, 2015 at 9:45 UTC. Here we are strain, and this is this incredible number of 10 to the minus 21, this thickness of a hair from here to Alpha Centauri, because the stiffness of space, that's the entire distortion that took place, versus this is a 10th of a second between pairs of tick marks. We saw this signal. Now let me talk a bit more about that signal. Yes, please.
Did you see that signal so clean, or you saw something else? The system was already operating and giving you this?
That's right. The system was putting out its noise as a function of time. The 2 systems were putting out their noise as a function of time, and then they both made this wiggle. And a thing I want to stress, I wonder how many of you know, this is a fun question that I like to pose, and of course I don't know how in French one says strip chart recorder. It's a nice old-fashioned device where you have paper that's being drawn out by a motor at a constant speed and a galvanometer with some ink pen that's always drying out, and you have to add more paint and wet it and so forth and so on. And it scratches as a function of time, the distortion of space-time. That's the kind of output that we get from LIGO. It's the strain as a function of time. I want to say this is a thing, Thibault talked about it, and it's something that he made enormous contributions to, which is the loss of energy to a binary system observed due to gravitational radiation. But this wasn't a measure of the instantaneous strain in space. It was a measure of the time averaged power radiated by the system. And the thing that's different about what we do is that we measure the change in distance between our own test masses as a function of time. And so it's the instantaneous amplitude. And from that, it means you can really make some astrophysical interpretations about the events that would not be possible otherwise. So I want to walk you through, this is a figure from the paper that we published as soon as we made, not as soon, once we'd finished convincing ourselves that we'd actually seen something, understanding what it was, and putting together a paper. This is one of the figures from that paper. I want to walk through it panel by panel, because I think it's a nice way of seeing encapsulated on one page what was measured. This is this curve that you've seen a couple times now. This is the output of one of our two detectors, the one up at Hanford. The signal processing that's been done is to cut out high frequencies and cut out low frequencies so that the very large motions at very low frequencies don't disturb us, and the noise which was above the signal frequencies at high frequencies doesn't mask it either. And just with that, you can see with your eye that there's something coming out of this detector that's extraordinary. This is a superposition of the outputs from our two detectors. The one from Hanford has been shifted by 7.1 milliseconds with respect to the other one. So here I have to say the distance between the two detectors in the United States is 10 milliseconds if you're a photon or a graviton. And so had the signal come directly along the line between the two of them, we would have seen a 10 millisecond difference. Had it been directly overhead, they would have been perfectly synchronized. You can see already, you can make somewhere in an annulus in the southern hemisphere was this source. With two detectors, that's all you can do. We need Virgo. That's what you need if you really want to pinpoint in the sky where a source is. You can see that the amplitudes are about right, and I think that's everything to say about that particular plot. Now here we come to something which touches directly on what Thibault was talking about. If you assume general relativity is correct, and you use the combination of the understanding of the analytical understanding of Einstein's equations, and you check them and cross-correlate them with the output from numerical relativity, you can make predictions of templates of the waveforms that could be emitted by a pair of black holes. If you search all of the parameter space for the first mass and the second mass, as well as the distance, and in fact assume no spins in this case, then you can come up with a template which is a best fit to the signals that we saw. And the template that works is the same for the two different detectors. If you take that template and you subtract it from this signal, you get this, which is nothing. And that's really what's astonishing here. It's nothing to the measure, of course, in which we have statistical certainty. There's still some noise here, so there's still some uncertainty. But so far as we can tell, Einstein's equations were correct for this. It's an event which involves nothing but space-time, and it works.
Because the scale looks like the same.
It's the same. Well, if we do an analysis of that, we can find no deviation from Poisson noise in that time period. Now, of course, we can do that only with some limited resolution. We can say we're 95%, I can't remember what the actual number is, sure that there's no power that is not explained by Einstein's relativity. We'll have to have better and better signal-to-noise ratios to make more and more stringent tests of general relativity. But to the extent that we can measure it, there's no deviation from general relativity. This is a spectrogram of the same thing. This is frequency versus time, and it's got this characteristic chirp format of first a slow in spiral, and then more and more rapid, and then the final coalescence leading to the end phase here. A thing I want to point out here is the ring down. This is something that Thibault talked about a bit. Let me back up a slide so I don't have my text in the way. After you reach the coalescence, one expects this resulting black hole to wobble like jello with a set of quasi-normal modes. And we would have loved to have seen convincingly this final phase. Try as we might, we cannot say with absolute certitude that we see what's predicted in this region. The signal-to-noise ratio is just not good enough. And that's something that is a near-term and really valuable goal to arrive at. And I'll come back to that when I talk about better detectors in the future. Now, I have a recording of the sound that I wonder if we have a microphone here that's turned on. And I'll put it next to my laptop as a poor man's audio interface. I don't have a movie, no. I suppressed all the movies. I thought they were too pretty for this crowd, but good. That's not the right computer. So what I'm going to show you now is we take the output of that photodiode from this detector, we put it through some high-pass and low-pass filters like the ones I showed you, and then put it into the loudspeaker system here. People say, oh, you can hear black holes. I'm going to be very careful. What we can do is to make a sonification of the strain in space as a function of time. You can't hear black holes, of course. And so what I'm going to do, it's going to play 3 times so that it's easy to hear. And the first thing you'll hear is the rumbling, low-frequency background of the instruments, which is there all the time. That's that noise that we saw when we subtracted the signal from the output of the detector. And then you'll hear the whoop sound of the gravitational wave as it shrinks and stretches space. That was not very impressive because it's too low frequency for the little loudspeakers in this Macintosh computer. However, what we're going to do now is to shift the frequency up by an octave so that you can hear it more clearly, and I think this will be much more impressive. And that may be something you've heard before if you were following the news around all of this nonsense, but the thing to think about again is that's the sound of 2 objects, each one tens of masses of the sun, whipping around each other at the speed that the blender in your American kitchen whirls around as they melt into one single object. It's an incredible notion. Was it real? This is the kind of thing, when a physicist sees something as remarkable as this, the first thing that you say is, it was a fluke, even though it appeared in both detectors, it's consistent with general relativity. This is not something you want to fool around with. We better wait till we have a little handful of them. We were very lucky to find, before we actually made a public announcement, although after we'd already convinced ourselves that we'd seen something, that we had another event. And this is, again, a pair of black holes. This is, again, that chirp-like structure. You'll see this is a lot less clear than the ones that I showed you on previous pages because the signal-to-noise ratio is not as high. And this is more the kind of signal-to-noise ratio that we thought we'd been dealing with. And whereas the previous result, I think Thibault mentioned this, was so strong that you could see it with your eye and you didn't have to use those templates to pull it out of the noise, this one really did require that template bank. You could not have seen this in the noise. In fact, it went by us, and it was in a post-analysis that we actually saw that there was a signal there. In fact, during the first observing run, we saw 3 things, 2.9, take your choice, of signals that were worth noting. This is, again, a plot of strain versus frequency. These are the noise figures for our 2 different instruments with the seismic noise, thermal noise, shot noise at high frequencies. And these are the paths in time for our signals. This is our first signal. It was a very large event, so relatively low in frequency at the point of coalescence. And it has this kind of characteristic signal versus time. The signal is actually getting larger up here, but it goes by more quickly. So the integrated power is lower. And that's what it looks like if you start counting from 30 hertz, which is about where we start to have a good enough signal-to-noise ratio to see something. To the coalescence, it only lasted for a couple tenths of a second. The other 2 events that we saw, one of which had the one that I just showed you, which has got also a 5 sigma for those who like that kind of measure of significance, quite a significant event. And then there's this one which is not nearly as loud, but it has to be a gravitational wave. All 3 of them are black hole events, and they took the same kind of trajectory through our frequency space. What's really fun now is that you can say, we're not just talking about an interesting and quirky proof that gravitational waves are as Einstein predicted them, but instead we can start talking about an astronomy of gravitational wave sources. One of the things you can see here, for instance, is black holes seen to date. There were a number of black holes that had been pretty unambiguously identified via X-ray studies, and then there are the things that we saw, which, and I think except for maybe a couple of these are of the same class of mass as this, but certainly the resultant ones are much more massive than anything else we'd seen, and there was an open question of whether or not black holes of this sort of 60 solar mass existed, in fact. But more impressively, you can really extract a great deal of information from the signals that we have to date. This is, for these 3 different signals, a list of the various different kinds of parameters that we've been able to extract from them. The signal-to-noise ratio and so forth and so on. The initial masses, as I said, these really break ground for what you could imagine the masses to be. There's the mass after the coalescence, and if you do the math here, you'll discover that there are several solar masses of energy that are turned into gravitational radiation. We were able to measure the spins, not very accurately, of the precursors because the events were face on or face off, you have to get it from the side if you want a really good measure of the spins for non-precessing spins. So we didn't have very much in the way of information on spins. I'll show you something on the next page about that. Radiated energy, peak luminosity, these are, of course, things that we infer using Einstein's GR as the point of departure, distance, and then our very poor sky localization that has to do with the fact that we had 2 detectors and a limited signal-to-noise ratio.
GW and LVT?
These we are proud to call gold-plated events. This is the terminology that we've chosen, LIGO Virgo transient object, as something for which we don't really have a claim of a full detection. We think, though, that there are going to be a lot of objects that fall below the level of certainty, but which will make important contributions to a sense of cataloging events. As Thibault says, it's not very interesting, but somebody's got to do it. Spins of component black holes. As I said, we'd like to make inferences about the origins of the black holes based on spin. After 2 objects coalesce, the object that's left behind is forcibly going to have a very high spin. So had our precursors shown a large spin, we could say they were made up of previous coalescences. In fact, none of our input devices, none of our input black holes had very high spins, and in only one case could we really identify a spin of 0.2. So we think these are probably primordial black holes that were formed as an isolated object star, which exploded and that was just too massive and collapsed down to a tear in space-time. This is a plot of the probability distribution of spin, and so you can see it's a little bit more than, most of the plots looked like this, where you couldn't really see anything about the spin. This one you really could say it's non-zero. So that's what we were able to do with these 2 detectors. We are very impatient that Advanced Virgo join us, and it looks like in the early spring they'll join the observing run that we've just started. The Kagra detector is very ambitious in terms of its technology in Japan. They project that they may start to be able to observe 2018. I think it'll be a bit later, 2020 or something like that. In India, an infrastructure is being built for a 3rd LIGO detector that we've already packaged up and is waiting for installation in this infrastructure. The current readiness state for that is 2024. And with that, we'll start to have enough detectors and spread enough over the Earth that we can do a better job of localizing.
Who's paying for India?
India is paying for its infrastructure, and the National Science Foundation will give the detector as a gift.
And why is it in India?
We want to get it as far away as possible. If you zoom out to Alpha Centauri and you look at the gravitational wave detectors, this one, and this one are pretty much all in a line. And as a consequence, you can't do very good localization. You'd like to put one down here, say. And we looked intensively at placing one in Australia. That didn't work out, and looks like the best place is India. But that, as I will show you in an instant, already makes a huge difference in our ability to localize. So what does the future hold? This is a recap of where we are for the first detections. We had 2 detectors. We're at about 1/3 of our goal sensitivity as we work down all those noise sources at low frequencies and increase the light power to improve the shot noise limit. We saw 3 signals in 4 months of observation. And on the sky, we have these huge banana-shaped uncertainty ellipses. So when we tell an astronomer, oh, we saw something, well, never mind. A pair of black holes, if there's no matter around them, shouldn't radiate anything in photons anyway. But even if they did, we wouldn't be able to tell them where they were because the uncertainty is so huge as to where these objects are. Please?
So what's the meaning of this?
This is the likelihood ellipses of the position of the source. So it was most likely to be in the center of this banana-shaped object here, or these are for 3 different sources, or in the center of this one here. There was some probability that it could be here or here. These are topographic maps of the likelihood of the position of the object. And you can see it's all over the map, as they say. When we add Virgo, a 3rd detector, we expect to have 1 to 2 signals per month of observation in this observing run that's now just getting started. And you can see now these bananas have shrunk down to cornichons. Now the uncertainty in position in the sky is much smaller, and there are even some places, if it were to be found at that point there, we could actually say fairly precisely where it was. if you're an astronomer, you know that those fields of view are still huge compared with most astronomical instruments. And still, it's a bit of a hunt for a needle in a haystack to tell an astronomer it's somewhere in the circle, but it's better than nothing. As we improve the commissioning of the instruments and we get to the full goal sensitivity, I think it was Thibault who said, we will be at the order of one binary black hole signal per day, if our understanding of the statistics are right. And I hope a host of other kinds of signal sources as well, neutron stars and then things we don't understand. That's what I really hope for. Then what really changes our uncertainty in the sky is adding India and Japan. Japan helps a bit, but the thing that really is key here is India. It opens up that triangle, allows you to do much better triangulation, and gets us down to most of the circles being smaller than 10 square degrees. And with that, an astronomer can really do something.
What were the red dots on the previous? There were red crosses on the previous slide.
I don't know. Somebody else's slide. Red crosses. Oh, you know what? I think they're funny points where we have no sensitivity. I think they're places where we have, you happen to run into nulls that, it's kind of fun to look at the antenna pattern of a detector. If you have the L sitting like this, if you have a wave coming from the top or from the bottom, you have a maximum sensitivity. If it comes along one of the arms, this arm doesn't change length at all. This one does, so you're down to half the signal strength. If you come in at 45 degrees, you don't either shrink or extend either one of the arms. So there's this little pinch at the 45 degree points. And I think this is a funny place where you run into pinches for the detectors that we have.
Sources on the sky.
Okay, sources in the sky which fall on that spot. Okay, good. So this is a slightly different vision of looking to the future, one which will take us further into the future than just to 2018, 2019. Advanced LIGO operating at full power, which we expect to be in 2018, 2019. Virgo should be in the same situation. Again, this is strain versus frequency, and this is the sensitivity curve that we predict. It's interesting to note the quantum noise is indicated by the purple. That's that shot noise at high frequencies and radiation pressure at low frequencies. And this is the thermal noise in that noisy coding. And the sum of those in quadrature gives you the net sensitivity. And for that gives a reach for binary neutron stars of about 200 megaparsecs and a black hole binary reach of about 1,000 megaparsecs or so. A thing I want to point out, talked about.
Can you explain what you mean by these reaches?
By reaches, yes. If you, for a signal to noise ratio of 8 and averaged over both polarizations and all directions, you can see a binary neutron star, 1.4 solar masses, to a distance of 191 megaparsecs.
How much time to travel?
I don't know.
Probably.
Yeah. What is it? I can't do it in my head. Ask Google.
Yeah, it's alpha 4 megaparsec, 400 megaparsec, which was the distance of the first event. So
yeah. Billions of light years. Yeah.
No, nobody could hear.
Okay, Eric.
So that was 600 million light years, if you do the calculation. Yeah.
What?
The 200 megaparsec that you have on the first one.
600 million years, okay.
Yeah. And then a thing to note, I said that I really wanted to be able to see the quasi-normal modes of the black hole that remains afterwards. Once we are fully commissioned, we'll go from what we had, was about a signal-to-noise ratio of 7 for the detection, which is not enough to say with certainty that it's there, to a signal-to-noise ratio of about 21. And so that's already getting to the point where you could perhaps make an unambiguous conclusion that we'd be able to see a black hole. Now, if we make some additions to advanced LIGO that we think we understand how to do, making cleverer use of the squeezing of light, the prepared states of light, to trade delta X against delta P in Heisenberg's equation, we improve the coding thermal noise with some ideas that look like they may pay off. That will bring us, you can see the difference between the sensitivity of these two curves, to a point where we go up to about 500 megaparsecs for the binary neutron star reach, and we move to, it now starts to talk more reasonable to talk about redshifts for the distance to the binary black holes. And the quasi-normal mode signal-to-noise ratio jumps to about 35 or so. So this is something we hope to have going in, say, 2022. Then we think about how we can exploit fully if we have an instrument that's 4 kilometers long or 3 kilometers long. Yes, please? We need to do the microphone, however. Where's the microphone? I've got it. Yep.
Thank you. On almost every plot of sensitivity, whatever the upgrade is, you have this kind of 3 peaks on the sensitivity. What they are for? It seems like resonances, or I don't know.
Yes, those are the resonances of the violin strings. We have these 4 threads of fused silica that hold our test mass up in space. And if you pluck them, they resonate with a harmonic series just like a violin string. So we call them violin modes. They're excited by the thermal energy. That's KT of energy. And that's an example of what I was talking about, a very, very narrow resonance which gathers the KT of thermal energy and holds the energy below and above out of the way. And so then the next thing that we might think of doing after we've fully exploited the infrastructures that we have, these 3 and 4 kilometer long systems, is to do something really new. In Europe, something that's been pursued to some depth is this Einstein telescope concept, which is to make an underground construction that has the advantages of reducing somewhat that Newtonian background I talked about, and certainly also reduces the seismic noise and makes it easier to handle. It's also a convenient thing in densely populated Europe to find a place that can house 3 buildings on the surface rather than tubes which block the migration of some rare species and that sort of thing. The notion is to make something which is a triangle. You make interferometers along all of the different arms, and that gives you sensitivity to both polarizations of the gravitational wave in a single place, and also allows you to make sums and differences of the lengths to be able to suppress some of the noise sources in the sensing system. And this notion is to build something which is really flexible. It could hold a whole number of interferometers filling the tube, some which are specialized for high frequencies to look at the final stages of a neutron star coalescence, some for low frequencies, which will be looking for, say, 1,000 solar mass objects. And it will use all of the tricks that we possibly can come up with at that time. In the US, we were talking about making something which is a little bit more, less subtle in terms of its approach. And that is to say, suppose we just took advanced LIGO and made it 10 times longer and used the same laser, the same room temperature optics, the same optical configuration, and so forth and so on. The signal would be 10 times larger. We're still in the short antenna limit, but almost all of the noise sources will remain the same. And in fact, some of them will even become proportionally smaller when you make the instrument longer. And so it's sort of a proof by reduction that you could build something which would be another 10 times more sensitive, not 1 signal per day, but 1,000 signals per day when fully commissioned, just by making it that much longer. It's an expensive thing to do. Among other things, the Earth is in the way. Over 40 kilometers, you have to move a fair amount of Earth just to make the vacuum pipes which keep the fluctuations in the arm length due to the atmosphere negligible. But you could imagine making something like this if there's a big enough community of people who think that this is a useful thing to do with science dollars. So here's a way of looking at the kind of sensitivity that you could get with these wonderful instruments. This is now, we're no longer talking about megaparsecs, we're talking about redshift in terms of distance. And these are distances for 10 solar mass on 10 solar mass black holes. Oh, actually, no, I'm sorry, I said the wrong thing. This is a curve, on the vertical scale is redshift, on the horizontal scale is the mass. For 10 on 10 solar masses, this is the kind of sensitivity you could have. If we were to find, again, a system with the same kind of characteristics as the ones that we first saw, let's just say 30 or so solar masses, and you wanted to look again at that signal-to-noise ratio in the quasi-normal modes, it would be something like a factor of 600. So you could really do very fine spectroscopy on the format of that final signal. And these are various different dreams. I mean, this is what advanced LIGO can do. It can see out to distances of, sort of a redshift of 1 or something like that for sort of 100 solar mass objects. But these other instruments, Einstein telescope or the US Cosmic Explorer concept, could see much further out. And in fact, these instruments should be able to see all of the coalescences of all black holes in this mass range in the entire universe. It should be able to reach all the way out to the edge of the universe. So we think we have ways, technical solutions, to really make an astrophysics out of this. So that third generation interferometer, when could it happen? We have a couple of points in experimental space. How long does it take from the time you have a firm concept for what you're going to build until it's actually running? It's about 15 years or so. That was true for initial LIGO, advanced LIGO, Virgo, and so forth and so on. So this means that you could imagine these kinds of fantastic instruments running somewhere in the mid-2030s. We should have these ready to go by the time LISA, the space antenna, which I'll talk about in just an instant, running, because, well, among other people, Dr. Sassana has noted, and I think it was Henri who mentioned, that you could see signals that came from a space instrument and then a ground instrument, and observe the two in one after the other. But really crucial for all these endeavors is to expand the scientific community that's thinking about this. A bunch of general relativists are not going to motivate a $2 billion investment in gravitational wave antennas. The cost of these things is similar to, the ELT here in Europe. It's sort of $1 billion. You need to have thousands and thousands of scientists who think that this is the key thing to make their science move forward. And so an important role for the people in this field is to spread the word about the kinds of things that could be done and then prove that we can actually do something with the instruments we currently have. The 30-meter telescope, the Giant Magellan telescope, and then the extremely large telescope. These are all these segmented mirror things that are currently either in construction or in conception. But that's big science. This is big science. Really big science. What is the cost of LISA? $2.1 billion is one estimate in which I have a bit of faith. So here, my one animation. What is LISA? The notion is, why not put an instrument in space? Oh yeah, sure. I mean, it's a distraction from the words, but that's okay. So the notion is to put an interferometer in space. We spend a lot of money making vacuum on the Earth's surface and getting away from seismic motion. So why not just throw the thing up into space, make the arms extremely long so that the signal is extremely large. It gives you very high signal-to-noise ratio. You also could observe very much larger masses because this limit of this sort of 1 to 3 hertz or so goes away. I'll play it again. And it allows us to see galaxies with black holes of, say, 1 million solar masses merging with 1 million solar masses. And it's analogous to adding radio astronomy to optical astronomy. So yeah, let's go back again. This is too much fun, right? So here's the concept of how it goes up. You send up a single rocket. In it are 3 pancake-shaped objects. Each one's identical. And each one contains 2 telescopes pointing at the other corners of an equilateral triangle, and a little bit of electronics and a couple of rocket motors, so that these 3 things can be positioned in space. And the notion is that you form an equilateral triangle, and you place it into orbit behind the Earth at the Lagrange point, which actually turns out to be pretty stable. And then you measure the distances between these 3 telescopes using laser beams. You don't do interferometry quite the same way that you do with the instrument on the ground for a variety of practical reasons. You basically do much more this timing experiment. Thibault was asked if space shrinks and your measurement system shrinks. This is a really realization of that. You send out a pulse of light effectively and see how long it takes to come back to you. And by looking at the differences in the different directions, you can infer the gravitational waves. And because the system scans the Earth, both in rotation and around the Earth, it effectively is in multiple places for any sources that last a time comparable to a year. So with it, you can resolve polarizations. You probably can resolve a stochastic background. That's iffier, but you can do localization in space. So this idea came out of a dinner. It's about as old as these other ideas. I think it was pretty obvious early on that the thing to do is to get it off the Earth's surface if you want to do some things. We take advantage of the vacuum in space. It moves its best sensitivity down to millihertz, as I mentioned. Triangular configuration. You take sums and differences around the triangle to get these polarizations and also to suppress laser frequency noise. Provides a scan of the sky, effectively all the things I just said. There's this beautiful, beautiful experiment that's currently flying, LISA Pathfinder. There was a lot of doubt. When you tell a space engineer you're going to measure a picometer, they say this is ridiculous, you can't do anything like that. But a space flight was recently undertaken, it's actually still going now, where two masses, each one a couple of kilograms, made of platinum gold, they had their position measured with a little interferometer, and we were able to demonstrate, or the people who did this experiment were able to demonstrate a performance which was far better than what had been anticipated and is actually good enough for LISA. So here's a fun plot. This is the strain amplitude, and this is the frequency, but now instead of being 100 hertz or a kilohertz or something like that, we're down to 10 to the minus 2 hertz, 10 to the minus 3 hertz, 10 to the minus 4 hertz. And there are a number of posited sources on here that have to do with things of 10 to the 6 solar masses. So you see everything has shifted to a completely different regime of mass. If you take the current LISA Pathfinder performance of holding two masses isolated from stray forces and being measured in position with a laser interferometer, and you lay it on this curve, you can see that they have been able to demonstrate a sensitivity which suffices to make this instrument work. And in fact, here's another fun illustration of that. If you take a calculation of what it would look like to have two 500,000 solar mass objects spiraling into each other on a LISA baseline, and then you take the LISA Pathfinder noise and you put it on the same figure at the same scale height, that's what the noise looks like compared with the actual signal size. You could do amazing things in terms of comparisons with general relativity and looking at the details of the interaction of the objects. It's an ESA-led mission. NASA is a minority partner for once. The US is in the back seat. There are discussions about how we'll put the entire mission together. Phase A is imminent. Mission adoption is possible in 2020. This, of course, is a shocking number. Launch date is nominally 2034. There are a number of young people in the room who will be around when this actually gets off the ground. But then the science that can be done is really formidable. So that's my story. We start out with these coalescing black holes through the intermediary of Einstein and his brilliance, not only in creating general relativity, but then also explaining to us how the photon shot noise works, how thermal noise works, led us to the ability to make this detection. Thank you.
Thank you very much, David. So, time for a few questions.
En français ou anglais, c'est OK.
On peut poser les questions en français.
What is your biggest challenge for the 4 years to come? Could it be the House Science Committee, whose the chair asks you for practical applications?
What is the biggest challenge? I heard that part, but I didn't hear what your postulated challenge was. Say again.
Quel est votre plus grand challenge pour les 4 ans qui viennent? Est-ce que c'est le House Science Committee et l'ARM Smith qui vous a demandé des applications pratiques?
Oui, j'ai peur de ça. Il se peut que ça va se passer. Je ne pense pas. C'est curieux, mais le soutien aux États-Unis, au moins pour la science fondamentale, est très solide parmi les républicains et les démocrates. Et donc, je pense que ça va toujours être considéré comme un très bon candidat pour développer les techniques de base qui pourraient être appliquées aux militaires ou je ne sais pas quoi plus tard. Mais je pense que ça va aller. Je pense que le problème est plutôt ce problème de convaincre la grande population des scientifiques que c'est suffisamment intéressant et pas simplement une démonstration pour des physiciens de quelque chose de curieux, mais plutôt un outil pour l'astronomie et l'astrophysique en général.
Oh, thank you very much. Je vais la poser en français. Vous avez parlé pour ELISA d'une variation de longueur de 10-12.
Oui.
Comme les satellites sont distants de 1 milliard de kilomètres, ça fait la même sensibilité que LIGO, 10-21. Le H
Exactement.
égale 10-21. Donc,
Oui.
il n'y a pas d'amélioration par rapport
Ouais,
à LIGO.
c'est le même H, mais
Oui.
les objets plus massifs font les H beaucoup plus grandes.
Ah oui.
Ça c'est la différence.
Oui,
On a multiplié
oui.
le masse par
Oui.
10 puissance 3 ou 4 ou quelque chose comme
Une
ça.
vibration toutes les
C'est ça. Mais
toutes les 1000 secondes.
Vous
Ma
avez
deux-
parfaitement raison,
ouais.
c'est le même H.
Ma deuxième question, c'est sur les ondes gravitationnelles.
C'est pour qu'il faut demander à Thibaut plutôt que moi, mais bon,
Oui.
allons-y.
Elles sont atténuées quand elles traversent un trou noir. Elles sont atténuées puisqu'elles bougent les molécules
Oui.
de la Terre,
Oui.
quand elles traversent la Terre, elles sont atténuées.
Il y a certainement un tout petit peu d'énergie qui est déposée dans tous les objets dans le chemin des ondes gravitationnelles, mais c'est minuscule, c'est complètement négligeable. Et en conséquence, c'est un des grands avantages des ondes gravitationnelles plutôt que les ondes électromagnétiques comme signal pour regarder très 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 loin. Ce n'est pas diffusé, ce n'est pas absorbé. Donc l'amplitude que nous apercevons est le même qu'un facteur, je ne sais pas quoi, complètement négligeable.
Oui. Et à travers un trou noir, qu'est-ce que ça fait? Ça la mange, ça disparaît.
C'est
ça...
un système complètement non linéaire, mais je ne crois pas que... Est-ce qu'on pourrait imaginer quelque chose
Donc ça pourrait sortir d'un trou noir.
Passe un trou noir? Je ne sais pas, je ne pense pas.
Bon. Après ça, une dernière petite question. Vous connaissez le continent, l'Aniakea, Hélène Courtois, vous savez, notre continent galactique de 500 millions d'années-lumière, une grande queue de comète qui va vers le grand attracteur.
Oui.
Dans le grand attracteur, 100 000 galaxies, 1 million de petites, chacune avec un trou noir, ça ne va pas faire des ondes gravitationnelles, tout ça, ça tourne.
Oui.
Et c'est pas très loin, c'est 500 millions d'années-lumière.
Plusieurs types de réponses. Je pense que dès qu'on a une distance au-delà de seulement le Virgo cluster, ou en fait aussi peu que, disons, 50 mégaparsecs, qu'une esquisse de masse contre distance est presque exactement ce qu'on attend, une montée linéaire avec la quantité de volume qui est inclus. Même qu'il y ait des formes de très grande taille comme ça, ça n'influence pas beaucoup la masse en fonction de distance. Peut-être une autre type de réponse est qu'en effet, LISA, peut-être LIGO même, mais certainement LISA, va souffrir d'un bruit de fond qui vient de tous les milliards d'objets qui sont en train de faire des bruits. Et c'est un grand challenge dans le cas de LISA de soustraire suffisamment de ces objets individuels avec des template fitting, etc., pour regarder plus profondément dans le bruit pour les objets plus exotiques. Donc, il y a certainement un fond stochastique qui vient de ça. Dernière chose, il y a certainement aussi un fond stochastique qui vient de Cosmic Microwave Background. Pas microwave, le Cosmic Background. Et ça serait fantastique à voir. Je ne pense pas que nous avons une bonne chance avec les instruments comme ça à cause de cette statique qui vient, comment on dit, le bruit de fond qui vient des beaucoup d'événements qui se passent tout le temps. Mais ce n'est pas impossible. Je pense que c'est question de B-mode polarisation. Regardez
10-40 joules pour un fond,
très
fond
difficile.
diffus. Oui.
Très difficile d'imaginer comment on peut faire ça.
Difficile. Merci.
De rien.
Merci beaucoup.
Oui.
Bonjour, c'est une question qui va peut-être vous paraître un peu naïve. Ce que j'ai compris, c'est qu'au départ, l'objectif de la détection des ondes gravitationnelles était la confirmation de la relativité générale. Actuellement, ce dont on a l'impression, c'est que les expériences que vous promouvez, qui se développent au fur et à mesure, en termes matériels, ont un coût marginal qui ne se justifie pas par une augmentation, disons, de la justification, une probabilité plus grande que la relativité générale soit confirmée. Je ne sais pas si vous voyez ce que je veux dire. C'est-à-dire qu'on va rajouter énormément d'expériences et de tests pour quelque chose qui est déjà prouvé à X%, et le pourcentage supplémentaire qui va être apporté, pour moi qui suis assez néophyte, je ne le vois pas. Est-ce qu'il y a des justifications extérieures à la relativité générale qui motiveraient, disons, même l'astrophysique en général, qui motiverait, vous voyez ce que je veux dire. C'est-à-dire que là, on est sorti du domaine de validation de la relativité, si j'ai bien compris.
Oui, c'est vraiment pas mon domaine. Je bâtis des instruments et je ne suis pas un expert sur la relativité générale. Donc, je ne peux pas vraiment répondre bien à cette question. Thibault pourrait dire, ou peut-être quelqu'un d'autre, mais je pense que ce qu'on pourrait... Ça serait fantastique de voir une déviation depuis la relativité générale, parce que ça peut amener à tout un niveau de conclusion alternative sur, par exemple, la dark energy, ou bien pour expliquer des autres problèmes en physique fondamentale, la connexion entre la gravitation et le monde quantique, par exemple. Pour le moment, ils sont complètement découplés parce que la structure d'Einstein est tellement simple et ça marche tellement bien. Et c'est vraiment fantastique, cet aliment. Donc, ces conflits pourraient être résolus si on peut faire une très petite mais certaine différence entre la relativité générale et les modélisations. Donc.
Excusez-moi de vous poser une question peut-être plutôt mathématique, mais d'après ce que j'ai compris dans le livre d'Einstein-Ilfeld sur le train, c'est linéaire. Est-ce que éventuellement le temps en réseau ne pourrait pas expliquer plus de choses que faire passer à des théories peut-être un peu plus nouvelles? Je ne sais pas si je me fais comprendre.
Je ne peux pas répondre à ça. Oui.
Non,
mais je pense que c'est hors de ma
Dans
domaine.
les théories d'Einstein, on parle quand même de la physique aristotélicienne qui est basée sur la ligne, sur le point, sur une géométrie tout à fait primitive, quoi. Si on veut dire, c'est pas de la topologie, c'est pas de la spationomie. Enfin, on pourrait supposer que si on a une expérience qui couple autre chose que linéairement, comme l'expérience d'aspect, par exemple. Je crois que l'expérience d'aspect, parce que vous parlez justement de la jonction entre la physique quantique et la physique à grande échelle, quoi. Grosso modo, c'est le grande échelle et petite échelle, ou échelle extrêmement petite et échelle extrêmement grande. Est-ce que le fait d'explorer l'espace en supposant qu'on ne connaît pas ce que c'est que l'espace, en ne se fiant pas directement à nos appréhensions géométriques qui datent de Thalès et d'Euclide, on n'arriverait pas avec des expériences, comment dire, ce dont parlait Einstein, c'est des expériences de l'esprit, mais transférées directement sur l'ordinateur pour... Vous voyez ce que je veux dire, quoi, non?
Oui, moi, j'ai aucune idée.
Alors, oui. Il y a une autre question là-haut, Bertrand, encore, et puis après, je crois qu'on va bientôt clore la session. Ou l'exposer, du moins.
Oui, je voudrais savoir comment vous pouvez... avez-vous pensé à insérer, par exemple, les observations du radiotélescope chinois qui a été dernièrement mis en marche avec l'aventure de la détection des ondes gravitationnelles?
Je n'ai pas compris les mots. Il faudrait dire peut-être un
Comment pouvez-vous... Est-ce que vous avez réfléchi sur la possibilité d'utiliser les radiotélescopes, notamment celui qui a été construit en Chine, avec ce que vous êtes en train de faire sur les ondes gravitationnelles?
La question est, est-ce qu'on peut utiliser les observatoires de... Oui. Il y a à peu près 65 équipes d'observatoires qui ont signé qui suivent nos signaux et qui cherchent une corrélation entre nos signaux et les signaux dans le champ électromagnétique pour essayer d'identifier quelque chose qui serait en commun entre les deux. Jusqu'à maintenant, on a vu des trous noirs, et s'il n'y a pas de matière autour de ces trous noirs, on n'attend pas jusqu'à maintenant qu'il y aura des signaux, des photons qui sont associés avec les gravitons. Mais on espère voir, par exemple, des étoiles neutrons ou une supernova, ça serait vraiment très chouette. Et dans ce cas-là, il y aura vraiment quelque chose à faire. Et donc, on observe avec beaucoup de monde. Jusqu'à maintenant, comme j'ai montré, l'incertitude dans le ciel est énorme. Donc, c'est très difficile de savoir où il faudrait regarder. Et donc, c'est un dilemme. Dans 5 ans, à peu près, on devrait être dans une situation de faire cette combinaison d'électromagnétique et gravitation, et ça serait vraiment bien.
Oui, on a un commentaire du prochain speaker.
Oui, pour compléter ce que David vient de dire, si on parle de radiotélescope en particulier, et en particulier le radiotélescope que vous venez de mentionner, des très très grands radiotélescopes, un des points qui vient à l'esprit, c'est vraiment tout ce qui concerne la chronométrie des pulsars, qui est une autre méthode d'aller voir les ondes gravitationnelles, je ne pense pas que Thibault l'ait abordé ce matin. Peut-être que j'ai passé ça. Donc c'est une des fenêtres qui va être ouverte sur les ondes gravitationnelles probablement dans les années à venir, au nanohertz. Là, on parlait du millihertz avec LISA, au kilohertz, à la centaine de hertz avec LIGO. Et le principe de détection est d'utiliser les pulsars, d'accord, ces horloges atomiques qu'on a dans notre galaxie finalement pour regarder les temps d'arrivée des pulses qui eux-mêmes donc, sont des photons qui se propagent du pulsar jusqu'à nous et qui sont donc sur leur trajet soumis aux effets des ondes gravitationnelles. Donc il y a des retards ou des avances à l'arrivée de ces pulses qui sont dus à la déformation de l'espace-temps sur leur chemin. Et en corrélant ces retards et avances observés sur plusieurs pulsars, on arrive à calculer la déformation de l'espace-temps sur leur chemin et donc à détecter les ondes gravitationnelles. Donc ça, c'est une autre manière d'utiliser les radiotélescopes pour les ondes gravitationnelles.
Merci, ce qui va nous donner la transition parfaite pour notre prochain orateur, qui est justement Éric Chassand-Motin.
Merci beaucoup encore à
David Shoemaker.
À David Shoemaker.